So we recently talked about one type of text similarity, specifically the one that is computed after stemming the words. We're now going to look at a different kind of spelling similarity, the edit distance. So very often people make mistakes when they go to a search engine. For example, they may want to be looking for pictures of Britney Spears and they type her name as Brittany Spears. So they often spell a name like Katharine Hepburn incorrectly, or spell the word receipt with I before E, even though they are well aware of the rule when you should use it one way or the other. There are also variants in spelling that I mentioned before. So theater can be spelled with ER or RE. We want to be able to capture the similarity between those spellings so that if a user types Britney Spears, we should be able to know that they meant Britney Spears because the two spellings are similar enough, and return the documents about her. So let me show you now a little funny example from a different language. I want you to be exposed to examples from as many languages as possible. Now, those of you who know Arabic can probably read this without any problems. But those who cannot, I'm going to give you some hints. So I want to ask you, can you guess with successive hints on my behalf who this person is? Arabic is spelled right to left. The symbol that I marked is pronounced M. This one is pronounced F. This combination of symbols is pronounced L or L. So there's a reason why I'm showing you this example. So can you figure out who this person may be? Well, it is Muammar Gaddafi, the former leader of Libya, who was deposed and killed a few years ago. So what is interesting about this example is that there are no common conventions on how to transliterate certain words like this. So this name has been rendered in the media as Muammar, M-U-A-M-M-A-R, or Muammar with one M and an O instead of a U. The word Gaddafi, his last name, has been rendered as G or KH, one D or two Ds, and so on. And then the middle Al can be omitted without changing the meaning of the name. So that results in a variety of different transliterations. So we can have the first name spelled in the following set of ways. M followed by either U or O, followed by A, followed by one or two M's, followed by an A or an E, followed by an R. The middle box shows you the different options for L. That could be either lowercase el, uppercase el, AL, uppercase AL, or blank. And then the third box shows you the spelling of the last name. So that gives us a total of 8 times 5 times 360, a total of 14,400 different combinations. Now, not all of those are used in the media, but I have seen more than 60 different ways of spelling this name. So if we want to find documents that contain references to the same person, we have to take transliteration and its issues into account. So in all the examples that I showed you so far, Gaddafi, theater, and Britney Spears, and so on, you may realize that the changes between the different versions of the word are not random or arbitrary. They are typically of the following form. They can be insertions or deletions. For example, the word behavior in British English is spelled with I-O-U-R at the end, and then in American English it's spelled with just I-O-R. So here, if we start from the British version and we want to convert to the American version, we would have a deletion. And then we would go the other way around if we go from American English to British English. This also applies to the word al in al-Gaddafi. Now, the other type of operation that is common in editing is substitution. So string and spring are very similar words. They have only one letter difference. So if we want to transform string into spring, we would have one edit operation, specifically one substitution. So in the Gaddafi example, this would be the swap of a K with a Q. Now, if we want to convert sleep to slept, we would need multiple edits. So think about the minimum number of edits to convert sleep to slept, if we are only allowed to have insertions, deletions, and substitutions. So one possible way to convert sleep to slept is to drop one of the E's and insert a T. So that's 2 operations. Or we can even possibly replace the second E in sleep with a P and to replace the P with a T. That's still two operations, but in some sense, the second one is less likely to make sense because you were inserting a p in one place and then deleting a p in another place. Now, one specific type of operation that is not shown here is a swap of adjacent letters. I'm going to talk about them in a few minutes. But in the meantime, let's stick to insertions, deletions, and substitutions of single characters. The method that is used to compute the edit distance between two words or two strings is often referred to as the Levenstein method. There are other names for it as well. It's based on dynamic programming. So it starts by computing the edit distance between two empty strings. And then recursively, it computes the edit distance between longer and longer substrings of the original words. And it uses costs of 1 for all insertions, deletions, and substitutions of length 1. Now let's look at an example. I picked two words, trend and strength. And I want to show you how the Levenstein method is going to compute the similarity between the two. So the way that it works is that you have to create a two-dimensional chart and then have 4 empty boxes in the upper left corner. And then you start by spelling one of the words across, starting with the cell where S of strength is located, going to the right. And then spelling the second word in the first column in position 3. And then the second row and the second column are numbered from 0 up until the length of those words. So in the first case, it's 0 to 8, and second case, 0 to 5. So Levenstein's method works like this. We're going to first compute the edit distance between the leftmost substring of strength, specifically the letter S, and the leftmost one-character substring of trend, namely T. So if S and T are those two letters, we're going to have an edit distance of 1 because they don't match. If they were the same, then we would have an edit distance of 0. And then we're going to compute the value of each of the cells in the table by making sure that we have previously computed the cell that is immediately above, immediately to the left, and immediately above to the left of the one that we want to compute. So at this point here, we can compute either the distance between S and T or any other cell for which we have those 3 neighbors already computed. But in this example, there aren't any. So we cannot really do anything but compute the distance from S and T. So the recurrence relation used in the Levenstein method uses the following definitions. So S1 sub I is the ith character in string S1. S2 sub j is the jth character in string S2. D sub ij is the edit distance between a prefix of S1 of length I and a prefix of S2 of length j. T sub I sub j is the cost of aligning the ith character in string S1 with the jth character in string S2. And let's see how those are computed. On the right-hand side of the slide, you see the base cases. D sub I0 is equal to I. So essentially, the cost of aligning any string of length I with a string of length 0 is equal to I, because we need I insertions to turn the empty string into the string of length I. So by symmetry, the edit distance between the empty string and a string of length j is equal to j, because we need j deletions to convert a string of length j to a string of length 0. And then finally, we have the recursive case. So to compute the edit distance between the substring S1 sub I and the substring S2 sub j, we need to compute the values of D for the cell above, the cell to the left, and the cell above to the left. And then figure out which of the 3 expressions shown in the min gives us the smallest value, and pick that one as the new edit distance. So in a sense, we can start from the cell to the left and add 1. We can start from the cell above and add 1. That would correspond to an insertion or deletion. Or we can start with the cell that is above and to the left, and then add either 1 or 0, depending on whether the ith character of string S1 matches the jth character of string S2. So the edit distance in the bottom part of the right-hand side tells you that t sub ij is equal to 0 if and only if the ith character of Si is equal to the jth character of S2. It's equal to 1 otherwise. Why? Because that would give us either a match, which has a cost of 0, or a substitution, which we agreed earlier would have a cost of 1. So let's look at our example again. To compute the edit distance between S and T, we said that it would be either the one above plus 1, which is 2, or the one to the left plus 1, which is also 2, or the one diagonally to the left and above, 0, plus the cost of substituting an S with a T. So of those three expressions, we have a 2, and a 1. The minimum one of those is 1. And therefore, we're going to produce this new value of 1 in the new cell. And now we can continue filling the table recursively. So the edit distance between ST and T, what is it? Well, we can either add 1 to the 2 above, which would give us a 3, or we can add 1 to the 1 to the left, which gives us 2, or we can start with the 1 that is diagonally above and to the left, and add to it the edit distance between T and T. Now, T is the same character as T, therefore their edit distance is 0. So to summarize, the smallest possible value in the cell that we're computing right now is 1. And we can do this now for the rest of the table. And at any point in time, we have to keep track of which path to that cell was used to compute the smallest distance. Let's look at one more example. If we have computed the table so far and we want to compute the edit distance of STR and TR, we can have the minimum of 2 plus 1, or 2 plus 1, or 1 plus 0, because there are r's in both strings in those particular locations. So we have a choice between the numbers 3, 3, and 1. So clearly we're going to pick 1 as the new value. And then at the end of the day, when we have filled the entire table, the number in the bottom right-hand corner is going to give us the edit distance between the two words. So in our case, that is 4. So strength is converted to trend by a minimum of 4 edit operations. And one possible way to do this is by dropping the S, replacing the G with the D, and then inserting a T and an H. There are other ways as well. So the edit transcript keeps track of the order in which the cells were computed, and we can use it to reconstitute the sequence of operations that converts one of the strings to the other. Now, people have proposed modifications to the Levenstein method. For example, Damerau proposed that swaps of two adjacent characters also have a cost of 1. And this is reasonable. In fact, the Damerau modification is commonly used in computing edit distance because it is linguistically motivated, and also it's motivated by user studies. People are likely to swap adjacent characters by accident. So the Levenstein edit distance between cats and cast would be 2, because we would either have to do 2 substitutions, or we would need to delete the T from one location and then insert it in a different location. So that gives us 2 operations, whereas the Damerau modification of this edit distance just has a score of 1, because it swaps ST for TS, which counts as 1 operation. Now, there may be some other distance operations that can be very specific to different tasks. Let me ask you the following question. Can you figure out why the edit distances for the pairs shown here are as indicated? So the first example is, why is the distance between sit clown and sit down equal to 1? So clearly, based on either the Levenstein or Damerau metric, we would have a cost of 2. We would need to drop the C and replace the L with a D. Well, in this case, according to some not yet specified edit metric, the distance is only going to be equal to 1. The second example, the distance between the word QEATHER and weather is equal to 1, which is understandable because we have one substitution from Q to W. But then the distance between leather and weather is equal to 2. Now, why do you think you would need to have a distance metric that makes this kind of assignments to the values? Well, I'll give you an answer in a second. Well, It turns out that those two edit distances are actually motivated by the process by which people create text. So in the first example, the distance between sit down and sit clown is very small because in optical character recognition, or OCR, it is possible to mistake the D character for a sequence of C and L. If you look at the two, they look pretty similar, and very often OCR software will make this kind of mistake. So if we want to recover from mistakes in OCR, we want to assign a relatively low edit distance between sit down and sit clown. There are other instances where OCR makes frequent mistakes. For example, the lowercase m in English can sometimes be interpreted as a little I followed by a little n. And there are many other such examples. Now, in the second example here, the distance between QEATHER and weather is smaller than the distance between leather and weather, because we want to model the way that people introduce spelling errors by using their fat fingers, essentially clicking on an adjacent key of the keyboard instead of the one that they wanted to click on. So Q and W are adjacent on the keyboard, whereas L is farther away. So if we want not to penalize people for making typos, we want QUEATHER to be considered relatively close to weather, because this is a very likely mistake that a user can make. Whereas substituting weather for leather is unlikely to have been caused by this fat finger process. So we want, in this case, to say that there is really a distance between those two words. Okay, now another quiz question. The Levenstein algorithms or similar algorithms based on dynamic programming are used not only for languages like English and Arabic and French, but also for other kinds of languages. Look at this sequence and think if you can recognize, maybe from high school or from some other source, what language it is in. You will see the answer on the next slide. Well, the answer is that this is a genetic sequence. It's not human language in the same sense as English or Arabic. It is still a human or a natural sequence. It can appear also in animals, obviously. The nucleotides that are encoded in the genetic sequence can only be one of 4 letters, A, G, C, or T, in the DNA sequences. So this particular sequence that I showed you is a well-known sequence, and I cannot even pronounce the name of what it represents, but it's something that you can look up in an encyclopedia of genetic sequences. So the method that I just described is based on dynamic programming, and it was used for aligning text sequences. But similar methods can also be used for aligning non-textual sequences. For example, nucleotide sequences, like in the previous example, where you have either DNA or RNA sequences consisting of symbols like ACGT for DNA and ACGU for RNA. But you can also have some special wildcards, such as dash, which stands for a gap of any length, and N, which stands for either one of the nucleotides. Similarly, one can use dynamic programming techniques for aligning amino acid sequences. For example, F, M, E, L, C, D, G, and so on, where each of the letters represents a specific amino acid, such as aspartate or glutamate or glutamine, and so on. In this particular case, there are also wildcards. X stands for any amino acid, Z stands for either glutamate or glutamine, and so on. And the costs of alignments here are determined empirically, and they reflect the evolutionary divergence between the different protein sequences. For example, aligning V and I is lower cost than aligning V and H. And for those of you who have a biology background, you can probably recognize the molecules of those amino acids. You can see that the valine and isoleucine molecules look very similar, whereas the histidine looks very different. So a few external demos. Levenstein demo is available at the URL shown on the top. And then I provide you here with a bunch of links to external sites that perform different forms of biological sequence alignment. And the NACLO problem related to this segment is called Knock Knock, which is spelled N-O-K, N-O-K. It's a NACLO 2009 problem by Eugene Fink. You can look at it on the external website, and then once you try to solve it, you can come back here. And now the solution for the knock-knock problem, it's again available on the external website. You can compare your solutions with the one that was officially accepted. And one more problem from NACLO related to sequence alignment. It's the lost tram problem, part of which I showed you earlier today. It's a NACLO 2007 problem by Boris Yomdin, and its solution is shown on the next slide. So this concludes the segment on edit distance using dynamic programming. We're going to continue soon with the next chapter of semantic similarity. Specifically, we're going to look at lexical similarity, synonymy, and other lexical semantic relationships.